Right, so last lecture we talked about the asymptotic behavior of the post-shock quantities as the Mach number increases. So for instance, if we have an oblique shock like this, and then we look at the pre-shock velocity, and then we draw here the normal to the shock. So then there is an angle here that is the incidence angle, and then the streamlines are going to be deflected. So then the post-shock velocity is going to look like this. And this angle here, the streamline deflection angle, is denoted by this delta. So for instance, in earlier discussions we were deriving expressions of the normal velocity, the ratio of the normal velocity components. So for instance, if one projects here the velocity to the normal, and here the same, then for instance one can write that the post-shock normal velocity divided by the pre-shock normal velocity is equal to 2 plus gamma minus 1 multiplied by Mach, the pre-shock Mach number square, multiplied by the sine square of beta minus 1, and then divided by gamma plus 1 multiplied by the Mach 1 square. This quantity that is here is also equal to the tangent of beta minus delta divided by the tangent of beta. At the same time, one can also construct, for instance, relations between u1 and u1n, right? Just by looking here at this angle. If this angle is beta, by symmetry, this angle is also beta, and then u1n is equal to u1 multiplied by the sine of beta. One can also do the same here and construct a relation between the post-shock velocity and the normal component of the post-shock velocity, which will be u2n will be equal to u2 multiplied by the sine of beta minus delta. Well, so one can take the hypersonic limit in these expressions and obtain simplified equations like the ones that we outlined in the last discussion. But here now we're going to do something different, and instead of looking at the normal component or the tangential component, we're going to look at the perturbation, at the velocity perturbations downstream of the shock. So for instance, if one has this shock wave, and this is the pre-shock velocity, then the question now is that we're going to have a deflection of the streamlines is going to be u2. And the question now is what happens with these two components, the horizontal component that I'm going to denote as small u2, and then the vertical component that I'm going to call v2. And this angle is delta. So the question is what happens with these velocity disturbances. The reason why one is interested in these velocities is that these velocities participate in the theory of hypersonic flows over the slender bodies. So there is a quantity that is important here, and is the velocity disturbance. That horizontal velocity disturbance is given by u prime, which will be equal to small u2 minus the pre-shock velocity. And then a vertical velocity disturbance v prime, which is going to be equal to just v2. It is also important to realize that these horizontal components are related to the post-shock velocity by this angle delta. So in such a way that u2 is just capital U2 multiplied by the sine, by the cosine of delta, and V2 is just capital U2 multiplied by the sine of delta. So let's try to obtain expressions for U2 and V2 as a function of this pre-shock velocity. So in order to do that, one can construct the ratio, for instance, of U2 divided by capital U1. So this ratio can be expressed as U2 divided by U2, capital U2, multiplied by U2 divided by U2n, multiplied by U2n divided by U1n, and multiplied by U1n divided by U1. So in this expression, for instance, we already know from this that this ratio is equal to the cosine of delta. This other ratio here, we already know from this equation that this is equal to 1 over the sine of beta minus delta. This velocity ratio, this normal velocity ratio here, is given by this expression here that you have on top. So this will be tangent of beta minus delta divided by the tangent of beta. And this other velocity that you have here, this other velocity ratio, can be obtained from here, right? So this will be just equal to the sine of beta. So in summary, this expression is equal to the sine of beta multiplied by the cosine of delta divided by the sine of beta minus delta multiplied by the tangent of beta minus delta and divided by the tangent of beta. Well, one can simplify this expression a little bit more, right? Here, for instance, by using trigonometric relations and by realizing that this entire expression, this entire coefficient that is here can be obtained, can be expressed in terms of tangents by using trigonometric identities. And this, in particular, this ratio that is here is equal to the tangent of beta divided by the tangent of beta minus delta multiplied by 1 divided by 1 plus the tangent of delta multiplied by the tangent of beta. In such a way that this ratio here is just equal to 1 divided by 1 plus the tangent of delta multiplied by the tangent of beta. Well, remember that one has an expression for the tangent of delta. This expression for the tangent of delta as a function of beta and Mach was derived in the last two lectures ago, right? And this relation is just that the tangent of delta is equal to 2 multiplied by the cotangent of beta and multiplied by the Mach 1 squared multiplied by the sine square of beta minus 1 divided by 2 plus the Mach 1 squared divided by gamma plus the cosine of 2 beta. One can insert this tangent of delta into this expression and then obtain that this horizontal velocity component of the post-shock gases can be written as 1 minus 2 multiplied by the Mach 1 squared sine square of beta minus 1 divided by gamma plus 1 multiplied by the Mach 1 squared. Right? Well, one can do exactly the same for the vertical velocity, and this vertical velocity v2 divided by u1 can also be written as v2 divided by u2 multiplied by u2 divided by u2n multiplied by u2n divided by u1n multiplied by u1n and divided by u1. These three ratios that are here are already computed up here, right? So this one, and this one. Whereas this one, the first one is different. And this one comes only from this relation here. This is equal to the sine of delta. So then this expression here is equal to the sine of beta multiplied by the sine of delta divided by the sine of beta minus delta and then multiplied by the tangent of beta minus delta divided by the tangent of beta. Or again, one can operate here with the trigonometric identities, right, to simplify this coefficient. And then at the end, one is going to obtain an expression like this, that is equal to the tangent of beta divided by 1 plus the tangent of delta multiplied by the tangent of beta. It should be the tangent of delta, sorry. Then if one substitutes again the tangent of delta from this upper expression, then one is going to obtain a relation, right, of beta V2 over E1 as a function of the Mach number and the shock incidence angle. So this relation here, right, can be written as the 2 multiplied by the cotangent of beta multiplied by the Mach 1 square sine square of beta minus 1, and then divided by gamma plus 1 multiplied by Mach 1 square. Right? So the question now, once that we have these expressions, is to again investigate what happens in the hypersonic limit. Remember that as we discussed, the hypersonic limit is a limit in which if one has here this wedge, we're interested in looking at a limit in which this Mach number, MA1, is large, but it's not only that the Mach number is large, the free stream Mach number, is that in particular the normal component of the Mach number is large. So that is to say that Mach 1 multiplied by the sine of beta is a large quantity. So if one inserts this, takes this hypersonic limit in these expressions for u and v, then one is going to obtain the following. So for instance, for the horizontal velocity, right, one is going to obtain the u2 divided by big 1, capital U1. Right, so I just need to take here the limit. This is going to be equal to 1 minus 2 multiplied by the sine square of beta divided by gamma plus 1. Whereas for the horizontal velocity, sorry, for the vertical velocity, it will be v2 divided by u1. That will be twice. So here I will have a cotangent of beta multiplied by the sine square of beta. So that is going to be equal to the sine of beta multiplied by the cosine of beta. And below I'm going to have a gamma plus 1. So if you recall from trigonometry, twice the sine of beta multiplied by the cosine of beta is equal to the sine of twice the angle beta. So this will be equal to sine of 2 beta divided by gamma plus 1. So these two expressions here are two expressions that are asymptotic expansions of these more complex expressions, but these are valid only for hypersonics. Well, if one looks at these expressions, right, the first thing that one notices, for instance, is that this velocity disturbance that I just defined here, right, this velocity disturbance that I just defined there, so it's going to be just 1 minus this entire quantity. I think one can notice here from this expression, right, that this is going to render velocity disturbance u prime, which is going to be of order beta square for a small beta. So if beta, remember, if the Mach number is large and beta is small, then beta and delta are similar, as we proved in the last lecture. And as a result, this order of magnitude here becomes of order delta square. Well, that this velocity disturbance in the horizontal direction becomes of order delta square is actually important for the theory of hypersonic flows over slender bodies. If you recall from the theory of supersonic aerodynamics over slender bodies, the horizontal velocity disturbance is linear with the angle, with the opening angle of the object, whereas here is quadratic, right? So that already tells us something about the nonlinear character of the theory that we're going to develop in the next discussions. So another quantity that is important here is the pressure coefficient, right? So for instance here, if I write now the pressure coefficient, this pressure coefficient is just going to be the pressure P2 minus P1 divided by 1 over 2 multiplied by rho 1 U1 squared. So here I can operate and express this as the following, just by dividing everything by P1, right? So I'm just going to do it probably slowly here. So this is going to be twice multiplied by P1 and divided by rho 1 U1 and U1 squared multiplied by P2 over P1 minus 1. Well, I think here everybody can recognize that I have something similar to a speed of sound, right? The speed of sound, remember that the speed of sound is just square is just gamma multiplied by P1 divided by rho 1. So obviously I have something similar to a speed of sound and a velocity square. Speed of sound square and velocity square. So I can construct there a Mach number. So if I erase this, and then I can write here twice divided by gamma multiplied by Mach 1 squared. Well, so for instance, this ratio, one can substitute this ratio from the Rankine-Hugoniot jump conditions. And then one would obtain that this is equal to 2 gamma multiplied by the Mach 1 squared. And then multiplied by 1 divided by, so it will be 2 divided by gamma multiplied by Mach 1 squared and multiplied by all of this. 1 plus 2 gamma divided by gamma plus 1 multiplied by Mach 1 squared sine square of beta minus 1, and here this minus 1 too. So I can again take here the hypersonic limit of this expression. And then I will have that this is going to be equal to 2 over gamma multiplied by Mach 1 squared. So this one and this one goes away. This is much larger than this other one. And then this is going to be equal to 2 gamma divided by gamma plus 1 multiplied by Mach 1 squared, in the first approximation, multiplied by the sine square of beta. So this Mach goes away with this Mach. This gamma goes away with this gamma. And then one obtains that this is equal to 4 divided by gamma plus 1 and multiplied by the sine square of beta. Right, so this is an important relation. Well, so I can also rewrite this pressure coefficient in terms of the velocity disturbance. So I think one is probably capable of recognizing that this sine square of beta, this function that is here, right, resembles a little bit this horizontal velocity, right? If I subtract 1 and I say 1 minus this, right? If I say 1 minus this quantity, then I'm going to get something similar to that, right? In particular, this expression can be rewritten as twice 1 minus U2 divided by capital U1. Or one could also write it as minus 2 multiplied by U prime divided by capital U1. Well, so this expression here, right, for the pressure coefficient, so equivalent. At high Mach numbers, what it tells us is that a negative velocity disturbance, right, a negative U prime, is going to generate a positive pressure coefficient. So in other words, if I look, for instance, at the same example as before, at this wedge, And this is again a high Mach number flow. Then I'm going to have a shock wave here. Then I'm going to have a pre-shock velocity U1. And then downstream of the shock, something is going to happen such that the horizontal component of the post-shock velocity is U2. The horizontal component of this velocity is going to be smaller than the pre-shock velocity. And as a result, the U prime is going to be smaller than 0. So in other words, across the shock, even though the total momentum is conserved, in the horizontal direction, there is a deficit of velocity as the flow crosses the shock. The horizontal component of the velocity is decreasing, right, with respect to the pre-shock gases. So this negative velocity disturbance, what it does is to generate a positive pressure coefficient and a positive pressure jump. And that generates a force on the wedge, and as a result, it generates a wave drag. So it is called a wave drag. That is only due to the pressure downstream of the shock. Well, so these techniques and these calculations, they look like very intricate and they look like complex and so on. But there is actually a much easier way of calculating pressure coefficients and drag forces on bodies. And we're going to look at this next. So what we're going to talk about here next is called the Newton's corpuscular theory of hypersonics. Sometimes this theory, depending on how one sees the derivation of this theory, tends to be quite disappointing. Because it is very, very simple, but it actually provides very accurate results, as we will see later. So let's start to think about how this theory is formulated. Well, so it was back in 1687 in the Newton's Principia, where among many other things he formulated this theory, particularly in the propositions 34 to 35. He envisioned the following when thinking about the mechanics of fluids. So he envisioned that one could have, for instance, this surface and then one would have, for instance, a stream of air here at some velocity u infinity, density rho infinity, and let's say a pressure P infinity. So then the question is, what is the force exerted on this surface? So the way that Newton thought about that was that the fluid, or the gas in this case, would behave like a collection of individual pellets or corpuscles. So each one of the molecules or corpuscles of air here will be traveling to the right, will all be traveling to the right, and they will be colliding against the surface, against this inclined surface. Well, of course, Newton envisioned that there were no interactions, no cross interactions between these corpuscles, right? So they would just approach the surface ballistically. For instance, this one would approach the surface ballistically, and then it would collide with the surface. So upon collision, at this point, this velocity u infinity can be divided into two components, right? One tangential to the surface and another one that is normal. So the tangential to the surface here is just u infinity multiplied by this the cosine of this inclination angle. That would be the tangential component. Well, these corpuscles will go to the surface, they will collide inelastically, and then they would slide down along the surface, all of them. It's just this one, two, right? In such a way that they would be giving away their normal component of the velocity, or what is the same, they will be transferring their momentum normal to the surface to the surface. So this velocity normal to the surface, this u sub n, is just the velocity at infinity multiplied by the sine of delta. Well, these the fact that these corpuscles are giving away their normal momentum to the surface, that obviously creates a force on the surface, and this force will go in this direction. So it is upon collision, upon inelastic collision, that all the collection of all these corpuscles in the gas that were the constituents of the gas were actually going to generate a force. Well, so for instance, if one tries to calculate that force, just by looking at this figure, this force is just going to be equal to the density rho infinity multiplied by the velocity u infinity, right? That will be the momentum per unit volume of the entire cloud of corpuscles here, and then multiplied by the flux of volume towards the surface. So that will be u infinity multiplied by the surface of this, by the surface area of this wall. This is the surface area. And then multiplied by the cosine. So let me just repeat this thing, right? Because I actually have to revise it. So this will be equal to the rho infinity multiplied by the normal component of the velocity. So because it is the momentum, the normal momentum to the surface, the one that is given away, and then multiplied by the flux, by the volume flux towards the surface. So this will be equal to rho infinity multiplied by u infinity squared multiplied by the sine square of delta and multiplied by s. Because here I'm just use this relation for the normal velocity. Well, so then one has an expression of the force as a function of this quantity rho infinity u infinity squared, as a function of the surface area, and as a function of the sine square of the inclination angle. Well, one can also say that this force here necessarily needs to be equal to the pressure minus the pressure at infinity multiplied by the surface area. And as a result, this pressure, right, the pressure on the surface of this wall, right, from this quality here, can be written as P infinity plus rho infinity multiplied by u infinity squared and multiplied by the sine square of delta. If one tries to calculate from here the pressure coefficient, the pressure coefficient is going to be equal to P minus P infinity divided by 1/2 multiplied by rho infinity u infinity squared. So I have to substitute here this pressure right there. So then the final result is going to be that this is going to be equal to 2 multiplied by the sine square of delta. This is perhaps the central result of the Newtonian theory. So in the theory of Newton, the force on this wall can be just computed by the simple expression of a pressure coefficient, right? That only depends on the inclination of the surface delta. Well, so this looks quite simple, right? It looks much simpler than the Rankine-Houonnet equations. It looks definitely much simpler than integrating the conservation equations across a shock and many of the concepts that we have been looking at in this discussion. So this is a very simplified theory. Well, obviously, this theory had its drawbacks. For instance, if one looks here for the viscous effects, there are no viscous effects in this theory. So it was much later than this year than the structure of a boundary layer was described, much later than this. And it was later than this year too than D'Alembert, for instance, calculated the drag on an inviscid, the drag on a body in an inviscid flow, and then realized too that there is a field around the body, right? In particular, there is a pressure field that, for instance, in subsonic aerodynamics becomes elliptic. So these corpuscles are no longer independent from each other. As a matter of fact, they should already be feeling the presence of the body far away from the body, for instance, at low Mach numbers, right? And that's given by the pressure field and by a field calculation of the mechanics of this fluid that came later with the Navier-Stokes equations. So this formulation that you have here also was not written originally by Newton in this form, but was written much later by Epstein, inspired by the theory of Newton in the 1930s in a paper in the Proceedings of the National Academies. Well, but still, this theory turns out to be very powerful for the following reason. If one takes, for instance, the wedge here, again, this example, one is going to have a shock wave. And then, as we discussed last time, this shock wave is going to be very close to the surface of the body. So there is going to be here a very thin gap that is called the shock layer, where the gas is hot. So here the Mach number again is going to be large. Well, so it turns out to be that even though in subsonic aerodynamics we know that the fluid is feeling the presence of the body well ahead upstream because of elliptic effects, it turns out to be that hypersonic velocities, the molecules of the gas, right, that are moving, for instance, here towards this body, they don't feel the presence of the body until almost they are close to the surface. So it somehow, this situation resembles the ballistic collision of the corpuscles in the Newtonian theory. So each one of these fluid particles, let's say, is going to go towards this wedge, and then it's going to cross the shock, and then it's going to get deflected along the surface in a manner that resembles the Newtonian theory. So somehow there is some resemblance between this and what Newton was envisioning. Of course, Newton didn't know anything about hypersonics, but it was, as I said later, that it was discovered that the theory of Newton holds some promise in hypersonics. So in order to see this, for instance, let's just look at a little bit more to this pressure coefficient. Well, so if one takes, for instance, the example of a flat plate to begin with. So let's say, imagine here that I have this flat plate, and it has a surface S, and then it's inclined at a local angle delta. So here I'm going to have again a high Mach number. As a result, here one is going to have a shock wave like this. close to the plate where the gas is hot. And then the gas here in this shock layer is going to get deflected in this direction. Well, so this hypersonic flow is going to generate a force, right, obviously on the plate. Before calculating this force, let's just remark here that in this theory of Newton, everything that is on the shadow of the incoming stream, right? So for instance, everything that is here on the shadow, this back surface, the theory assumes that the pressure along that back surface is going to be P infinity, the same as in the free stream. So this is to say the following is that here, if one wanted to calculate the pressure coefficient for this flat plate, one wouldn't go and calculate here the Prandtl-Meyer expansion fan, but one would just say that the pressure in the back surface is just P infinity, and as a result, the pressure coefficient on this surface is going to be equal to 0. Well, that's also an approximation, right, of the theory, and it's an approximation too, such that it becomes accurate when this pressure P infinity is actually much smaller than the pressure that develops on the surface of the plate. For instance, in the case of hypersonic flows, if these two pressures are more or less similar, for instance, as in subsonic aerodynamics, that they differ only by amounts that are much smaller than the static pressure at infinity, then this assumption here actually becomes really bad. But remember that most of the wave drag on an object flying hypersonically is caused by the front surface. The second thing that I wanted to say is that the calculation of Newton's pressure coefficient that you have here is only a function of the local surface inclination, delta. So it's only a function of this delta. As a result, this method, the Newton method, belongs to a class of methods of computing forces in hypersonics that are called local surface inclination methods. There are more than just the Newtonian theory, but we are going to see only the Newtonian theory here. It is to say that the only thing that you need to do to calculate the pressure coefficient is just the inclination, the local inclination of the surface, which actually simplifies the problem a lot. So if we go back to this derivation here, so for instance here I could compute the force on the plate. This force here is going to have a component which is going to be the drag force in this direction, and then a lift force in this direction. So if this is delta, then this is also delta. And as a result, one, for instance, can say that the drag force is going to be just the pressure, P minus P infinity, multiplied by the surface projected on the vertical, right? So that will give me just S multiplied by the pressure projected on the surface. So that will be the sine of delta. So in other words, if I substitute the relation for the pressure that Newton proposes, or before doing that, if I go and I just calculate the drag, define the drag coefficient as the force, the drag force divided by 1/2 of rho infinity u infinity squared, and then here as a reference surface, I'm just going to take the total surface of the plate, S. So then it is not difficult for you to see that this substitution of this expression here, right, and calculation of the drag coefficient, I'm going to tell you that this is twice multiplied by the sine cube of delta. So the drag coefficient varies as the cube of the sine. Then I can do the same too for the lift coefficient. So I can define the lift force as P minus P infinity, and then this time multiply by S and multiply by the cosine of delta. And then again define the lift coefficient as the lift force divided by 1/2 of rho infinity E infinity squared and multiply by the reference first, that is S. This is going to give me twice multiply by the sine square of delta and multiply by the cosine of delta. Well, if one looks at these expressions here, together with the pressure coefficient, one realizes here about a couple of things. The first one is that this drag force, obviously, right, it becomes a maximum when delta is just when this delta is pi halves. So when the plate is just normal to the stream, this maximum, you get a maximum drag, right? However, when the plate is parallel to the stream, this expression here tells me that the drag coefficient is 0. Well, that the drag coefficient is 0 when the plate is parallel to the wall is not actually what happens in reality. What happens in reality is that when the plate is parallel to the stream, there is a boundary layer that develops around the plate, and then you have a drag force acting on the plate, which is of viscous origin. Right. So as one turns the plate, right, and makes it horizontal, obviously some of this theory is going to break down. Particularly, one could, for instance, see that the critical angle for this theory to break down is an angle such that this drag coefficient becomes of the same order as the friction coefficient, as the skin friction coefficient for a hypersonic boundary layer. So for instance, if I were to take this drag coefficient and equate it to a classic skin friction coefficient for a hypersonic boundary layer, these numbers here for the skin friction coefficient, they tend to be of the order of 10 to the minus 3. So if I obtain from here delta, you can calculate that this delta will become 4 degrees. So that is to say that as soon as the inclination of the plate is about 4 degrees or less, then you may expect viscous effects to come into play here, which are not considered in any of this. Well, so for instance, for the same reason, if I look at the lift force when the plate is vertical, right, then the cosine of pi halves is 0, and as a result, when the plate is normal to the stream, the lift force is 0 according to this expression. And also, when the plate is horizontal, the lift force becomes 0 according to this theory. And we can see this thing in the chart. So for instance, here you have a delta in the horizontal axis. The solid line is the lift. The lift has a maximum at an angle of about 55 degrees. That's the optimum angle that produces the largest lift coefficient. And then one thing to notice also that is important is that the drag goes more rapidly to 0 than the lift at 0 angles of incidence, and as a result, the lift over drag goes to infinity when the plate is aligned with the stream, right? So you see there the lift over drag curve diverging at the small angles delta. So if we go here, right, this lift over drag is going to go like the lift coefficient divided by the drag coefficient. This lift coefficient actually goes like delta square, whereas this drag coefficient goes like delta cube when delta is small. So as a result, this lift over drag is going to go to infinity. Well, again, that will happen when the plate is horizontal. So the fact that the lift over drag goes to infinity when the plate is horizontal is an artifact of the theory, because one is not including any viscous effects here. Another thing that is important to notice in this formulation is that the drag coefficient, for instance, here, according to this expression, for a small delta is of order delta cube. And this pressure coefficient for a small delta is of order delta square. Well, this is in contrast, for instance, to the theory of linear supersonic aerodynamics. If you recall, in the theory of linear supersonic aerodynamics, the pressure coefficient around a slender body goes like twice multiplied by delta and divided by the Mach number square minus 1. So this is the pressure coefficient for instance, for a slender wing in supersonic aerodynamics. So this pressure coefficient goes linearly with delta, whereas in the Newtonian theory it goes quadratically with the angle, and already tells us important details about the nonlinearities at play here. Well, so how do we use this, right, in practice? So let's just go over some examples. For instance, let's just consider, for instance, the case of a wedge. Again, I'm interested in a wedge that has an angle of 30 degrees. Right, and this is going to be a wedge at high Mach numbers. So obviously, here I'm going to have these oblique shocks, right? And then let's say that here, let me call this Mach infinity. Here I'm going to have a P infinity, a rho infinity, and a U infinity. So I'm going to have a pressure jump, and here I'm just going to be changing the notation slightly, because I'm going to be calling the pre-shock quantities by the subindex infinity and the post-shock quantities by the subindex 2. So this is to say that here I'm going to have a pressure P2, and that pressure P2 obviously is larger than the pressure P infinity, and that generates a force on the wedge. In particular, this pressure P2 over P infinity can be described by using the Rankine-Hugoniot jump conditions as 1 plus 2 gamma divided by gamma plus 1 multiplied by Mach infinity square sine square of beta minus 1. In this case, this angle beta here, as we know, is going to be a solution of the problem. So the solution of the problem is obtained by imposing this streamline diffraction angle and by using the relation of tangent of delta is equal to twice cotangent of beta multiplied by Mach infinity square sine square of beta minus 1 and divided by twice plus Mach 1 square multiplied by gamma plus the cosine of 2 beta. Right, so with this, one can solve the problem. If I have delta, I can obtain beta, and if I have beta, I can enter here and obtain P2. With this, I could come here and obtain the pressure coefficient as 2 divided by gamma Mach infinity square and multiplied by P2 over P infinity minus 1. Right? And I could plot this in order for me to obtain the drag force. The drag force here is going to be just simply P minus P infinity multiplied by the cross-sectional area here, right? Whatever area I can pick, doesn't really matter, going to be the area A, because what I'm going to do next is to calculate the drag coefficient. The drag coefficient is just going to be P FD divided by 1/2 of rho infinity U infinity square, and then multiplied by this cross-sectional area here. So as a result, the areas and the areas, they go away, and then I have P minus P infinity divided by 1/2 of rho infinity U infinity squared, right? And this is just the pressure coefficient. This is just to say that when the inclination angle is constant, the drag coefficient and the pressure coefficient are the same. So I could compute, for instance, all of this as a function of the Mach number, and this is what you see in the chart. For instance, in this chart, you see in the horizontal axis the Mach number and then the drag coefficient. Well, the drag coefficient calculated from the Rankine-Hugoniot equations, right? So this drag coefficient is going to depend on the Mach number for some range of Mach numbers, but you see that it's attaining a sort of a plateau or a independence range in which the solution does not depend anymore on the Mach number or depends very little, right? Well, so one could, for instance, compare this with the Newtonian solution, right? The Newtonian solution, the only thing that one needs to do is to come here, right, and say that the drag coefficient will be just twice multiplied by the sine square of delta, right? And then one would obtain exactly the same. One could solve this, substitute here delta, right, and obtain the drag coefficient. And then you see the result in the next slide. That will be the result from the Newtonian theory. Well, so here you can see a little bit of discrepancy between the Newtonian theory and the Rankine-Hugoniot equations, right? So we are talking here about discrepancies of the order of 20%. But it is remarkable that the Newtonian theory is more or less in the same ballpark as the Rankine-Hugoniot equations. If I go back here to this form of the Newtonian theory drag coefficient or the pressure coefficient, right, to the original form that we wrote here, this form that you see here does not depend on the Mach number, right? So this is a quantity that is independent of the Mach number. And turns out to be that that is a very good assumption, because at high Mach numbers, the forces on the object become independent of the Mach number. And that's a very important result. At high Mach numbers, the pressure coefficients and the drag coefficients become independent of the Mach number. And this happens with the forces, right, on the object at hypersonic speeds, because most of the force on the object is generated by the wave drag, by the pattern of shock waves around the vehicle. And those shock waves, they impose a pressure field. That pressure field tends to be kind of insensitive to the Mach number at very high Mach numbers. This result, right, that I just mentioned, you can see back in the chart. It is manifested as that plateau in the drag force, and it's called the Mach independence principle. And if you recall, it has some easy explanation here, is that if I have a normal shock, for instance, like that, I know from the conservation of normal momentum that the quantity P1 plus ρ1 U1 squared, in this case, let's call it infinity to be consistent with the rest of the variables, is going to be equal to P2 plus ρ2 U2 squared. As I mentioned in earlier discussions, at high Mach numbers, the static contribution of the pressure upstream of the shock is negligible, and downstream, the kinetic contribution in this momentum is actually, this momentum flux is actually negligible. So the amount of build-up pressure, the amount of post-shock pressure that you can build downstream of the shock is imposed by the flux of momentum upstream from the shock. So there is only so much pressure that one can build, and the higher the Mach number, the closer these two numbers are. Well, so for instance, one can try to solve a similar problem. Instead of having here a wedge, right, one could try to solve the same problem for a cone. Let's say here that now I have a cone. If I have a cone there, right, so still this is going to be beta. Well, this expression here for the Rankine-Hugoniot jump condition for the pressure is going to be valid But even though one would be tempted to solve the problem similar to this, right, and disappointingly one would arrive to the same solution as the solution of a wedge, the problem of the cone is very much different than the problem of a wedge. And we will see that later. But in this case, for a cone, even though the post-shock pressure just right downstream of the shock, that pressure right downstream, pressure P2, is given by the Rankine-Hugoniot equation, the azimuthal curvature of the cone, right, in this direction, what it does is to generate a pressure relief, and that pressure relief effect is actually two-dimensional, such a way that this expression here for the tangent of delta, if I attempt to solve this expression, this delta actually is kind of a useless angle, because this will be the streamline deflection angle just downstream of the shock. But that wouldn't be the streamline deflection angle of the streamlines all along the shock layer. So this streamline deflection angle actually varies with distance for the problem of a cone. So this problem here needs to be solved numerically, and we will learn how to solve it. There is a theory that is called the Taylor-McCall theory, whose results you can see in the next chart. So for instance, here we are comparing the Taylor-McCall solution for a cone and the Newtonian theory. And here the discrepancies are a little bit smaller for the Newtonian theory. We are talking now of discrepancies of the order of 5 to 10%. Well, so one can go and try to solve a more difficult problem beyond a cone, right? One can try to go and solve a problem of a sphere. For instance, let's go here. So imagine for a second that we have a sphere, right? This sphere is in a flow at high Mach numbers. So this sphere is going to generate a shock wave, right? Which in the Newtonian approximation, this shock wave is going to be actually very close to the surface. As a matter of fact, it's going to be the surface. So one thing that you may have noticed too in this expression here for the CP is that there is no angle beta. So everything is only dependent on the local surface inclination. So what is the shock wave, right? So one may wonder, what is the shock wave in Newton's theory? Well, I will anticipate here that the shock wave in the Newtonian theory is actually the surface. So the surface and the shock, they become one in the Newtonian theory. And as a result, only the surface inclination angle is important. So if I look here back to the problem of a sphere, let's assume that this sphere has a radius r. And I'm interested, for instance, in calculating the drag coefficient. This would be the shock. Everything that is on the back of a sphere is in the shadow, right? So as a result, I don't care about the drag on the back of a sphere, because the pressure coefficient along all of this is going to be 0. So here I can define an axis z, coordinate z, right? And I can start operating. So the first thing to notice here is that I'm going to have an inclination angle delta. Let's draw this thing correctly. Going to have an inclination angle delta. And I'm going to have another angle here that I'm going to be using for operating, which is going to be theta. Well, this angle, local inclination angle, now the situation is different than the problem of the wedge and the cone, in the sense that this angle now delta depends on the position along the sphere, right? So that is going to make the problem a little bit harder. So, but here, for instance, I can see that if this angle is delta, then this angle is going to be 90 minus delta, and then this angle here is going to be again delta. So I can see that theta plus delta is equal to pi halves. And as a result, the sine of delta is going to be equal to the cosine of theta. The reason why I'm operating with theta is because I'm going to be using here spherical coordinates. So, for instance, if I go here and I plot again the z-axis, and here I go and I plot y-axis, and here is going to be the x-axis, I'm going to be looking at an element of surface like this. Going to be located from the center at some radial distance r, which is the radius of a sphere, which if I project it on the plane xy, it's going to have an angle from x to the projection of r onto the plane xy, an angle phi. So this element of surface here is going to be noted like this: a differential of surface going to be a vector, right? So in particular, the drag force is just going to be the minus integral over the surface of the sphere of the pressure minus the pressure P infinity multiplied by that element of surface projected on the minus z direction. So this E is a unit vector in the z direction, and the minus sign means that I'm actually looking at the force on towards the left, towards the right. So this differential of surface that is here, right, can plot it later, but I'm going to define it later. But for now, let's say that I'm interested, for instance, in calculating the drag force, right? So the drag force is just going to be the force, the drag coefficient is going to be just the drag force divided by 1/2 rho infinity u infinity square, and then here as an area, as a reference area, I'm going to choose the cross-sectional area. So that is the mean, that is to say the area of the circle, PR square. So if I develop this is going to be equal to the integral of P minus P infinity divided by 1/2 of rho infinity u infinity square. And here we have the element of surface multiplied by the unit vector in the z direction and divided by pi r squared. So I need two things here. I need to define this element of surface. In order to define this element of surface, I can just look at this from the differential geometry of this element of surface. I can tell you that for instance, the area of this is going to be just this segment here, this arc, right? That arc is just r multiplied by the differential of this angle theta. This angle theta plays the role of the complementary of latitude angle, and as a result, this segment here is just going to be r multiplied by the differential of theta. And then the other segment that I need to calculate the area is the transversal segment. This transversal segment, I can project it onto the plane, right, here, right, and then this radius of curvature, this radius here of this, the radius of the sphere projected on the x and y plane is just going to be r multiplied by the sine of phi. Sorry, r multiplied by the sine of theta. So that will be this component. Right, so then this is going to be equal to r d theta multiplied by r multiplied by the sine of theta multiplied by d theta multiplied by d phi. So this segment that you see here is just going to be r multiplied by the sine of theta multiplied by d phi. So this is to say that the element of surface is just r squared multiplied by the sine square of theta multiplied by d theta and multiplied by d phi, and this element of surface is going to go into the radial direction. So then I could come here, right, substitute this into the formula for the drag and say that the drag is equal to an integral, which is going to be a double integral. The pressure minus the P infinity is given by this quantity here is just the pressure coefficient, and here I can replace it, the pressure coefficient, substitute it from the Newtonian theory which is just twice multiplied by the sine of delta, right? Remember, this pressure coefficient comes from the Newtonian theory, right? But since it is written in terms of delta and I'm doing all the operations in terms of theta, I can write this as twice multiplied by the cosine square of theta. So here we have 2 multiplied by the cosine square of theta. Then I would need the element of surface that I have here, right? This element of surface is just going to be r squared multiplied by the sine square of theta. Then I need the product of the element of surface multiplied by the z direction. So this vector here, the element of surface multiplied in a scalar way with this vector, unit vector here, obviously is going to give me a cosine of theta, right? After doing the scalar product of those two vectors. So here I'm going to have another cosine of theta. Here there is no square of theta, it's just r squared sine of theta. And then we have here d theta, d phi, and divided everything by pi r squared. The limits of integration of this integral is in the case of phi, which is a longitudinal angle, right? This phi is going to have to go from 0 to 2 pi. And in the case of theta, theta only goes along the region that is exposed to the flow. So that will be from, for instance, from 0 to pi halves, or you could also do it from minus pi halves to pi halves. So from 0 to pi halves, right? And from 0 to 2 pi, I'm already covering the half of the surface of the sphere. So if I do this calculation here, this is just the integral, right? It's going to be just 2 pi multiplied by r squared divided by pi r squared. And then here I'm going to have the integral from 0 to pi halves of the cosine cube of theta multiplied by the sine of theta differential of theta. So if I perform here this calculation, I think I have forgotten a 4 somewhere. I have forgotten a 2, and I have forgotten a 2 of the 2 pi, because here I had a 2, right? And then with the 2 pi, this should be a 4. So this is a 4 here. So then if I perform this calculation, this is going to be 4. Here I can cancel this, right? The integral of this is just a potential integral. So this is going to just give me 4 multiplied by the minus 4 multiplied by the cosine fourth of theta divided by 4 from 0 to pi halves. And this integral here is going to give me 1/4, because the cosine of pi halves is 0, right? So it is going to be only non-zero at 0. So it's going to give me minus 4 over 4. So with a minus from the evaluation of the cosine fourth, this is going to give me equal to 1. So that is to say that the Newtonian drag predicted by the Newtonian drag of a sphere, right, is just equal to 1 when the reference area is taken as the cross-sectional area of the sphere. So, well, how does this drag coefficient perform? Well, so just look at the chart. So here, for instance, we have the drag coefficient on a sphere versus the Mach number, together with experimental data from Charters and Thomas and from Hodge. So you can see that there is a sort of a ramp at the beginning and a spike, that it is obviously related to conditions going through transonic flow, and then a decay and a plateau in the drag coefficient. That plateau in the drag coefficient in experimental data is again representative of the Mach independence principle. And then the Newtonian theory is there above the experimental data, probably at 10% higher than the experimental data. Well, if we go back to this development, one of the problems that it was discovered, right, with the Newtonian theory, and it was discovered by Lester Lees, in 1955, was that mismatch that you have just seen in the drag coefficient. Sorry, we go back to the chart. The Newtonian theory tends to overpredict the drag force by some amount, which is about 10%, right? So the question is, why is the Newtonian theory doing that? So there was work by Lester Lees back in the 50s. I realized that if one looks at the Newtonian theory, right? The Newtonian theory says that the pressure on the surface, if we have a blunt body like this, then the pressure on the surface is just the pressure at infinity plus rho infinity multiplied by u infinity squared. Here the inclination angle is 90 degrees, so if I were to put here the sine square of delta, this number will be 1. And then he realized that this surface pressure that is predicted by the Newtonian theory is actually higher than the pressure that one would obtain if one were to look here at the problem of a shock wave, of a bow shock around this blunt body, and then one would wonder about what is this post-shock stagnation pressure. So remember that if I zoom here, right, close to the surface, what one sees is a sort of a stagnation point flow. It will be the shock wave. Stagnation point flow in which the flow kind of recovers the stagnation pressure. As you can imagine, the wave drag on this blunt body is going to depend very much on whether one captures this stagnation pressure correctly or not, right? And it appears that the Newtonian theory wasn't predicting it correctly. So one can see this, for instance, by taking this expression and dividing it by the post-shock stagnation pressure, or what it is. Yeah, so one could do this, right? Substitute here and say that is equal to P infinity plus rho infinity U infinity squared divided by PO2, and this is going to be equal to P infinity divided by PO2 and multiplied by 1 plus gamma Mach 1 squared, Mach infinity squared. So in order for me to know what is the ratio of the Newtonian pressure on the surface to the real post-shock stagnation pressure, I have to derive this expression, right? So I have to here substitute the pressure ratio from the Rankine-Hugoniot jump conditions. So this pressure ratio can be just calculated like this: PO2 divided by P infinity going to be equal to PO2 divided by P2 multiplied by P2 divided by P infinity. This pressure ratio here comes from the isentropic relations, and this other one here comes from the Rankine-Hugoniot jump conditions. So this will be just 1 plus gamma minus 1 divided by 2 multiplied by Mach 2 squared gamma to gamma minus 1, and then this other one will come from the, so I said, from the Rankine-Hugoniot jump conditions. That will be 1 plus 2 gamma divided by gamma plus 1 multiplied by the Mach 1 squared, Mach infinity squared minus 1. Right, so one can take the expression for the Mach 2 here, right, for the post-shock Mach number from the Rankine-Hugoniot equations, and obtain the following expression. We obtain that this ratio will be equal to gamma plus 1 squared multiplied by the Mach infinity squared and divided by 4 gamma multiplied by Mach infinity squared minus 2 multiplied by gamma minus 1 multiplied by gamma power to gamma, gamma minus 1, and then multiplied by 1 minus gamma plus 2 gamma multiplied by Mach infinity squared divided by gamma plus 1. So with this ratio, right, this ratio is a function of gamma, one could substitute it here and then obtain an expression for the pressure Ps divided by P infinity, by the stagnation pressure in the post-shock gas. So if one does that, then one is going to obtain that the post-shock, that the surface pressure predicted by the Newton theory divided by the post-shock stagnation pressure is just equal to 1 plus gamma Mach infinity square multiplied by gamma plus 1 square multiplied by Mach infinity square divided by 4 gamma Mach infinity square minus 2 multiplied by gamma minus 1. All of this will be power to minus gamma divided by gamma minus 1. And then here we also need to multiply by another factor. By 1 minus gamma plus 2 gamma multiplied by the Mach infinity square and divided by gamma plus 1 to the minus 1. Well, so if one goes and plots this ratio, right, you're going to see it in the chart. This is the pressure on the surface predicted by the Newton theory divided by the stagnation pressure in the post-shock region that should be recovered close to the nose of the blunt body. So here you can see that the pressure ratio decreases and reaches an asymptote at high Mach numbers, and that asymptote is given in the screen and is equal to 1.09. So this is to say the following, and it is that the ratio of pressures in the Newtonian theory at high Mach numbers, the Newtonian theory overpredicts the pressure on the nose of the blunt body by a factor of 1.09, which is about 10%. So it was Lester Lees that with a theory that is called the modified Newtonian theory that said, well, so how about we construct a modified Newtonian theory such that the surface pressure equals the stagnation pressure downstream of the shock. And he did that by reformulating the pressure coefficient and saying that the pressure coefficient is equal to Cp maximum multiplied by the sine square of delta, where this Cp maximum is equal to PO2 minus P infinity divided by 1/2 of rho infinity U infinity square. One can obtain an expression for the Cp maximum just by taking here and operating and saying that this is equal to 1 divided by gamma, 2 divided by gamma Mach infinity square, and then multiply by PO2 divided by P infinity minus 1. So I just derive this ratio P02 over P infinity from here. I just need to substitute here the Cp maximum, and the curve of Cp maximum, you're going to see it in the screen. It looks like that, and actually attains another asymptote at high Mach numbers that is equal to 1.84. So this is to say that when the Mach number is large, the Cp maximum goes to 1.84. Remember that in the Newtonian theory, the Cp maximum plays the role of these two here. So I have a new modified Newtonian theory now from Lees that says that this prefactor instead of being 2 is 1.83, 1.84. Well, so what happens when one operates with this modified Newtonian theory? Well, let's see it in the chart. So if one modifies the Newtonian theory and uses the theory of Lees, right, then you can see that with this Cp max, the Newtonian theory goes over the data and actually matches very well. Well, so there are more corrections that one can do in the Newtonian theory, and we will see another correction that is related to centrifugal forces in the next discussion.